In this video, we work through 7 different problems that are related rates problems. We start with example 3. A piston is seated at the top of a cylindrical chamber with radius 5 centimeters when it starts moving into the chamber at a constant speed of 3 centimeters per second. What is the rate of change of the volume of the cylinder when the piston is 2 centimeters from the base of the chamber? First off, if you don't know what a piston is, you're going to have a really hard time doing this problem. A piston is sort of like an upside down ice cream push pop. If you can remember those orange ice cream things from your childhood, where you basically had this sort of cylinder which contained ice cream, and it had this plastic disc on the inside, and you push the little stick up, and as you push the stick up, the ice cream came out the top. So the more you ate the ice cream, the higher up you pushed it. A piston is sort of like that, only upside down. So what we basically have is some kind of container which contains the piston, and it comes down inside of the chamber, and it's pushing the gas that's inside the chamber into a more confined space. So usually we have a metal plate here at the top, right along this edge, and it's pushing down and it's compressing this gas-air mixture that you see here. So this would be our before picture. Then at a later point in time, the piston has pushed the air into the container until it takes up less volume. So even though the container itself does not change size, the place where the piston is pushed down has compressed the air into a smaller volume of space so that you have a higher pressure of the volume and air gasoline mixture. So what's happening is the radius of this is not changing, but the height or the depth of it is changing. Let's now take a look at the words. Remember that we read it the first time just to get a vague idea of what kind of problem it is. And then after reading it the first time to get a vague idea of what kind of problem it is, we go back and we break apart the parts of speech in the problem until we can translate roughly every 2 to 3 words and convert it into some kind of expression or equation or labeling on a picture. So going back to the words, we have a piston, which is basically the rod part with the metal plate attached, is seated, got it, at the top, okay, of a cylindrical chamber. A cylindrical chamber basically means that we have a cylinder at the top and a cylinder at the bottom, and it's connected on the sides. So it's sort of like a Coke can in shape with radius 5 centimeters. The radius is never going to change since the thing is made out of metal. So you can label that on both of your pictures that the radius is 5 centimeters. That's in both the before and in the after pictures. When it starts moving, got it, into the chamber, okay, at a constant speed, yes, of 3 centimeters per second. Now you have to decide how the piston is moving in, what's changing. Speed is a derivative. It's the change in some length with respect to time. When you look at the before and the after picture to its right, you can see that the height of the gasoline and air mixture inside of the chamber has changed. So what's changing here is the height. That means that when we measure the speed of the piston moving, we're measuring the rate of change of the height with respect to time. Since the height is getting shorter, that means the rate of change will be negative. So we have dH dt is equal to a negative 3 centimeters per second. Now we need to figure out what it is they're looking for in this particular equation. Second sentence, What is the rate of change of the volume of the cylinder when the piston is 2 centimeters from the base of the chamber? Back to the beginning. This is what I'm looking for, the rate of change of the volume of the cylinder. Rate of change of the volume is dV dt when, this is the moment in time, the piston, got it, is 2 centimeters, yes, from the base of the chamber. That's when the height is equal to 2 centimeters. When I have that information, I know I've completed the problem. Now I look at all the information I've written down and I try to come up with an equation that relates the information that I see in front of me. I have a V for volume and an H for height, and I know it's a cylinder. I know the radius of the cylinder never changes and it's 5 centimeters squared. The next thing I want to do is come up with an expression that relates the volume, the radius, which never changes, and the height. The equation that I come up with is the volume of a cylinder, which is the area of the base, pi r squared, times the height. Since my r never changes and is always 5 centimeters, I can replace r with 5 centimeters, square it in the formula, and I get 25 pi centimeters squared times h. This is the relating equation that relates the volume to the height. In order to complete the related rates problem, the next step is to take the implicit derivative, take the derivative on the left with respect to time and the derivative on the right with respect to time. In this case, we don't have too many variables, so we end up with dV dt is equal to 25 pi centimeters squared dH dt. Remember that h is a variable which changes with respect to time, so it doesn't just become a constant 1. We have to use the chain rule, which gives us 1 dH dt. Now that we have this, we can plug in the particular situation we're looking for, the change in volume with respect to time when height is equal to 2 centimeters. Notice in the equation, though, that height doesn't actually enter into it. It only is dependent on the rate of change of height with respect to time. It wouldn't matter if the height was 2 centimeters from the bottom or 4 centimeters. The change in volume only depends on the change in height with respect to time. This gives me 25 pi centimeters squared times dH dt, which is -3 centimeters per second. This gives me a final result of -75 pi centimeters cubed per second. Now I compare the units and ask myself if these units make sense for dV dt. V should be measured in volume units and centimeters cubed is volume. Time should be measured in seconds or minutes or hours, and its seconds does work. Then I ask myself, does this answer make sense? Does it make sense that if the height is decreasing and getting smaller, that the volume is getting smaller and decreasing? That makes the volume's rate of change negative. The answer is yes, it does. As the height gets smaller, the volume gets smaller, so it should be a negative rate of change. Now let's look at the next problem. This next problem can actually be rather challenging to set up. The situation is not entirely clear from the read, and you will have to make a couple of assumptions about what is happening. Let's read through it and see what assumptions we have to make. A jet ascends at a 10-degree angle from the horizontal with an airspeed of 550 miles per hour. Its speed along its line of flight. How fast is the altitude of the jet increasing? If the sun is directly overhead, how fast is the shadow of the jet moving on the ground? First off, notice that we were actually asked for 2 pieces of information. how fast the altitude of the jet is increasing, and how fast the shadow of the jet's moving on the ground. This is like two problems in one. Second, about the only other information I got out of this was that I had a jet in the air. That's about it. I didn't get much else. So now I'm going to draw a picture of what I have. I must have the ground down here somewhere. So I can draw a tree to indicate I've got the ground and maybe a house to go along with it. And then somewhere up here in the air, I have an airplane that was flying along. And then the airplane decided to go up at a 10-degree angle. A jet ascends. Ascends means to go up at a 10-degree angle from the horizontal. It was flying straight across. Now it's moved up 10 degrees. That means that the angle that the airplane is flying at has changed. And yes, I know my airplane looks like a cat with one ear, but that's my all-purpose vehicle, which is a plane. It moves at a 10-degree angle from the horizontal with an airspeed of 550 miles per hour. Its speed along its line of flight. That means that the speed in this direction as we move along is 550 miles per hour. That sounds like a derivative because it is a derivative. It's the rate of change of this distance with respect to time. Let's give this side a name so that we can write the derivative of it. We'll call it z. That means that dz dt has got to be 550 miles per hour. Since it's going up, we'll call it a positive 550 miles per hour, as in a positive rate of change. This is the change of z with respect to time. Now let's look at the next sentence. How fast, which sounds like a speed again, which of course is a derivative, is the altitude of the jet increasing? Here's where we have to make our first assumption. It's not clear whether they're talking about the altitude from the ground or the altitude from the horizontal. However, notice that the horizontal does not change its position with respect to the ground. So in essence, it's about the same thing. That means that we can just measure it from the first location, from the horizontal where it was flying. That means that this distance here is h. As time goes by, h gets larger and larger. How fast is the altitude of the jet increasing means we're looking for the rate of change of the height of that triangle with respect to time. And because it is increasing, we expect the rate of change to be positive. Now let's take a look at the second question. If the sun is directly overhead, unfortunately, I don't have much room left in my picture, so I'm going to have to put the sun up here sort of in the words. So the sun is directly above my airplane, casting a shadow of the jet on the ground. How fast is the shadow of the jet moving on the ground? Well, the shadow of my jet is going to be down here on the ground. And I want to know how fast the shadow is moving as it moves across this way as the airplane flies up at a 10-degree angle. I need to have some kind of measure of distance along the ground. I can call this distance down here x, and notice it would be the same if I were measuring up here on the triangle. That is the change of x with respect to time. In other words, how fast the shadow is moving on the ground is dx dt. And whether it's on the ground or on the horizontal portion of that triangle, it's essentially the same. We can also consider it to be positive as it's moving towards the right. We've reached the end of all the information that was given in the problem. The rest of it will have to come from you. You will have to come up with an equation that relates the information you've already been given. I know something about dz dt. I want to find something about dh dt and dx dt. I need to relate for the first part my z and my h. Looking at the triangle, I can relate h to z with the sine of the angle. I know that the sine of 10 degrees is equal to h divided by z. I can solve this for h to get h equals z times the sine of 10 degrees. This is what we would call the relating equation. This relates h to z, and when I take the derivative of both sides, I'll get their related rates. The next thing I want to do is take the derivative of both sides to get the related rate. This tells me that dh dt is equal to dz dt times the sine of 10 degrees. Notice that the sine of 10 degrees is a constant which does not change value. I know what dz dt is. It was given to me that was 550 miles per hour. That tells me that I can find dh dt by replacing dz dt with 550 miles per hour and multiplying it by the sine of 10 degrees. When I do the computation, I end up with approximately 95.5065 miles per hour. This is the answer for the first part, which is how much was the altitude changing with respect to time. Now we want to consider the second part, which is how fast is the shadow moving along the ground. To do that, I need to relate what I was given, x, to either h or z. I was given information about z, and I can relate x to z using the cosine of that angle. Now, there are actually two options that are available to you here. You could relate through cosine directly to z, or you could relate x to h using tangent. Both would work, and both will give you the correct answer. But keep in mind that the one with z will be more accurate because the z value given is exact, 550 miles per hour. The answer you just got for dh dt is approximate, 95.5065. However, you could make it accurate by using 550 miles per hour times the sine of 10 degrees instead. Let's write the two relating equations down now. Pause the video, write the relating equations, take the derivatives, and solve the problem. Then turn the video back on to see if your answer matches mine. Let's take a look at what you get for option 1 and option 2. When looking at option 1, you write the equation cosine of 10 degrees is equal to x over z. This is coming from the triangle where the adjacent side over the hypotenuse gives you the cosine of 10. Then you can solve for x and get x equals z cosine of 10 degrees. Take the derivative of both sides, then replace dz dt with 550 miles per hour to obtain 541.644 miles per hour. What about option 2? Option 2 uses the height, which is going to be less accurate unless you use the intermediate value. This would relate height and x using tangent, so that the tangent of 10 is h over x. Once we have that, we can solve for x again, and we get h over tangent of 10 degrees. Then we take the derivative of both sides of the equation, noting that tangent of 10 degrees is a constant. I use the intermediate value, 550 miles per hour times sine of 10 degrees, since that's a precise value. And that gives me the more precise value for dx dt, which is precisely the same 541.644 miles per hour that I got using option 1. Let's take a look now at the next example. This is an absolute classic example in terms of related rates problems. You see these all the time in textbooks. I don't know what it is about ladders, but they love the ladder problems. Let's read through it and see what it says. The problem reads, a 12-foot ladder is leaning against a vertical wall when David begins pulling the foot of the ladder away from the wall at a rate of 0.2 feet per second. What is the configuration of the ladder at the instant that the vertical speed of the top of the ladder equals the horizontal speed of the foot of the ladder? That is, what is the height of the ladder against the wall at that point in time and the distance of the foot of the ladder from the wall at the same instant? Well, there was a lot there. And really all I got is there's a ladder leaning against a wall and it starts moving out from the bottom. That means that I need to draw a picture. So when I draw my picture, I'm going to draw a wall. Over here, maybe I've got a door. Now, there is an assumption that you can make about walls and problems like these, and that is that the wall is at a right angle to the ground. This is not the Leaning Tower of Pisa. You need to draw the ground so that when you draw the ladder, it'll make more sense. A 12-foot ladder, got it, is leaning, got it, against a vertical wall. Go ahead and draw your 12-foot ladder and label it as 12 feet. When David, got it, begins pulling, okay, the foot of the ladder, so David is down here, and he's pulling on the foot of the ladder away from the wall, okay, at a rate of 0.2 feet per second. This distance right here, we can call X. He's pulling away from the ladder, which means it's going this way or away from the wall. Let's do an after picture where afterwards the ladder is lower down and David is still here, pulling the ladder away from the wall. Now we can see that this distance right here, which is X, is longer. Since it is longer, that means that it's increasing. And since it's increasing, I can write that as a positive rate of change. dx dt is equal to a positive 0.2 feet per second. Now that's not the only thing that's changing. Note that the top of the ladder is also changing, as in the height of the ladder, but it's decreasing and it's coming down the wall. What is the configuration of the ladder at the instant? Okay, by configuration of the ladder, they mean what is the height of the ladder against the wall and what is the distance of the foot of the ladder from the wall. In other words, they're looking for height against the wall and X, the distance of the foot of the ladder from the wall at some point in time. What point in time? When the vertical speed of the top of the ladder, what's the vertical speed? Speed and velocity are derivatives. Vertical speed at the top of the ladder has to be the rate of change of the height with respect to time. Speed, however, is the absolute value of velocity. So I want to know when the absolute value of dh dt is equal to the horizontal speed of the foot of the ladder. That would be the absolute value of dx dt. So I want to know what h and x are when I have the value of each speed being equal to the other. That means they're both in absolute values. That's all the information that comes from the problem. There's nothing more there. The rest of it's going to have to come from you. The equation that relates x and h to the 12 feet has to come out of your head. When you're looking at it, you had to make the assumption that this is a 90-degree angle, because what you need to use is the Pythagorean theorem. Once you have that, you have an equation that relates the h, the x, and the 12 feet. Let's go ahead and write that down now. I need a little more space. All right. So based on my picture, I have that x squared plus h squared is equal to the quantity 12 feet squared. This tells me that x squared plus h squared is equal to 144 square feet. Now I have a relationship between x and h. I want the instant when dh dt is equal to the magnitude of dx dt. That means I need to find dx dt and dh dt from my equation. The next thing to do is to take the derivative of both sides using implicit differentiation. Remember that x and h are both changing with respect to time. The next thing that I'm going to write is the derivative of the left, which is 2x dx dt plus 2h dh dt, which is equal to 0. Why 0? Well, 12 square feet is, or 12 feet squared, which is 144 square feet, is a constant. And when you take the derivative of a constant, you get 0. Now I know, because I've got a common factor of 2 on each of the two terms, that I could divide out the 2, and this would lead to the next equation, which is that x dx dt plus h dh dt equals 0. Now I want to know when the two have the same speed. I'm told that dx dt is 0.2 feet per second, but I know that dx dt is increasing. And I know that dh dt is decreasing. But if they have the same magnitude, that means their absolute values are equal. So I can replace dh dt with a negative 0.2 feet per second. That makes the second term negative. And when I move it to the other side of the equation, I get x times 0.2 feet per second equal to h times 0.2 feet per second. Then I can cancel the 0.2 feet per second from both sides, and I know that the magnitude of their speeds will be equal when the two sides are equal. That is, when x is equal to h. Then I can go back to my original equation that related x and h, and I can find out how long x and h are when that occurs. Since I had from this starred equation right here that x squared plus h squared equals 144 square feet, I know that when they're equal, I can write x squared plus x squared equals 144 square feet. This gives me 2x squared equal to 144 square feet. Remember, I'm trying to find h when the speeds are equal and x when the speeds are equal. So I need x and h, which are equal to each other. I can divide both sides by 2 to get x squared equal to 72 square feet. Then I take the square root of both sides. Normally, this would give me plus or minus the square root of 72 feet. However, I know x is a distance, so it can't be negative. 72 is 36 times 2, so I get that x is the positive 6 square root of 2 feet. Since X and H are equal, then I know that H is the same as well. That means that my answer to both parts is 6 square roots of 2b. Let's now take a look at the next problem, example 6. Sand falls from an overhead bin and accumulates in a conical pile with a radius that is always 3 times its height. Suppose the height of the pile increases at a rate of 2 centimeters per second when the pile is 12 centimeters high. At what rate is the sand leaving the bin at that instant? All I got out of it was sand falling. So I need to think about how sand might be measured. And then I can go back to the beginning of the problem and I can start writing down all the bits of information that are contained. Remember that you want to divide your problem up into the parts of speech: the subject phrase, the verb phrase, prepositional phrases, subordinate clauses, conjunctions, and punctuation marks. For those of you not excellent at English, go about every 2 to 3 words and stop and ask yourself, do I need to write something down? Let's start at the beginning. Sand, got it. Falls, okay. From an overhead bin. First thing you ought to do is draw some kind of box that's filled with sand. And accumulates, okay. Well, the sand is falling, okay. And accumulates, piles up, in a conical pile. Okay, so I've got this cone-shaped pile down here with a circular base with a radius. Okay, so I've got a radius of my circle that is always, okay, this means something that's never going to change, 3 times its height. Now, it doesn't mean that the radius doesn't change. It just means that the radius is always 3 times the height. So whatever the height is, the radius is 3 times that. In other words, my picture is way off. If the radius is 3 times the height, then it ought to be a pretty short, squatty, but very round radius like this, where the height is coming down from up above and measured at a 90-degree angle to the base. I've completed all the information from the first sentence. Let's move to the second one. Suppose the height of the pile, okay, that's H, increases, that means is positive, at a rate, so that's dH dt, of 2 centimeters per second when the pile, draw a long vertical bar to say when it's occurring, is 12 centimeters high. That's when H is 12 centimeters high. So obviously this isn't a whole lot of sand, but it's some sand. At what rate? Well, that's a derivative again. So I'm looking for a derivative of some kind. Is the sand, okay, leaving the bin, okay, at that instant? So I've got to think about at what rate the sand is coming out, but how do I measure sand? When I think about measuring sand, I don't think about measuring sand. I don't say I have 3 feet of sand. I might say it's 3 feet deep, but I don't say it's 3 feet long. When you go to buy sand, you buy sand in cubic yards. In other words, sand is measured in volume. So when it asks at what rate sand is leaving the bin, it's looking for the rate of change of the volume of sand with respect to time. And we're looking at the volume of the sand that's coming out. Now, what we're really looking at is the amount of sand that's piling up down below. If we're looking at the rate of change coming out of the bin, it should be negative. If we're looking at the rate of change piling up in the conical pile, it's getting bigger, so it should be positive. Keep that in mind when you're setting up your problems. We're trying to figure out what dV dt is at that point in time, which is basically when h is equal to 12 centimeters and dH dt is equal to 2 centimeters per second. Now we need some kind of equation that relates R, H, and V. That would be the volume of a cone. Since a cone is basically like a pyramid value, then we take the area of the base, pi r squared, multiply by the height, and then divide by 3. In other words, our formula is 1/3 pi r squared h. Now we have a problem. This equation relates V, R, and H, but I only have information about dH dt, and I'm looking for dV dt. I don't have any information about dr dt. Can I get rid of the R in the equation and replace it with something in terms of only H? The answer is yes. Because the radius is always 3 times the height, I can replace R in the equation with 3H and square it. That will give me 9H squared to replace R squared, and that gives me 3 pi H cubed as my equation. Now that I have 3 pi H cubed equal to the volume, I can take the derivative of both sides and solve it. Go ahead and pause the video here, complete the implicit differentiation of both sides using the chain rule, work out the solution, then turn the video back on to compare your answer to mine. What did you get? Since our equation is V equals 3 pi H cubed, you apply the chain rule to H cubed. That gives you 3 coming to the front to multiply by the constant 3 pi, reduce the power on H by 1 to H squared, then using the chain rule, multiply by the derivative of the inside function, dH dt. Then we can plug in the specific information. Remember to always do the derivative before you plug in the specific constants that you were given. We were told that H is 12 centimeters and dH dt is 2 centimeters per second. This gives us 2,592 pi cubic centimeters per second. Now, the cubic centimeters make sense for a change in volume, and seconds make sense for a change in time. Does the positive value make sense in this situation? And the answer is it depends. If you're talking about the change in volume of the pile, then yes, it does. The pile is getting larger. If you're talking about the rate of change of the sand from the bin, it should be a negative 2,592 pi cubic centimeters per second, since it's decreasing. Now let's take a look at another very classic and very common example of a related rate. This is a water tank, which has been inverted and is a conical water tank. An inverted conical water tank with a height of 12 feet and a radius of 6 feet is drained through a hole in the vertex at a rate of 2 cubic feet per second. What is the rate of change of the water depth when the water depth is 3 feet? Well, first off, let's label what we have from our problem. Starting at the beginning, it says an inverted conical water tank. You can see here in the picture on the left that we have an upside down cone. Looks like an ice cream cone with a height of 12 feet. This height of 12 feet is referring to the height of the tank itself. The height of the tank is not going to change. The tank is always going to be 12 feet tall. And a radius of 6 feet. Again, this is referring to the radius of the tank. And the radius of the tank is never going to change either. It's going to be 6 feet. Is drained, got it, through a hole, okay, in the vertex. In other words, there's a hole down here at the pointed part where water is escaping at a rate of 2 cubic feet per second. Look at the units that you have here on the 2 cubic feet per second. It's got to be a rate of change of volume. So we have a dV dt. Do you think the volume of water is increasing or decreasing as water drips out the bottom? Of course, it's decreasing. That means that dV dt must be a negative 2 cubic feet per second. Now we need to read the last sentence to figure out what we're trying to find. What is the rate of change of the water depth when the water depth is 3 feet? Rate of change, okay, that's a derivative, of the water depth. I don't have anything in my picture yet that measures the height of the water. I'll use a lowercase h to represent the water height. This lowercase h will change. As water comes out, the water level will drop inside the tank. It will not stay the same. Find the rate of change of the water depth, dH dt, which I'm expecting to be negative because I expect it to drop when the water depth is 3 feet, when the height is equal to 3 feet. Now I've written down all the information for the problem. I need to come up with an equation that relates the information I'm given. I'm given that the radius of the tank is 6 feet, the height of the tank is 12 feet, and the height of the water is varying. There is another variable that is in this equation that's not entirely clear from the beginning, and that's the radius of the water layer in the tank. The water layer has its own radius, which we can use a lowercase r to represent that. If you look at this particular tank and you were to take and drop a line going through the center of the circle down through the vertex of the point, and then come straight across and straight down the side, you could create a right triangle. That's the right triangle you see over here in the right-hand picture. The radius along the top is 6 feet. That's the radius of the tank, which is never going to change. The full measure of the height of the tank is also never going to change. It's 12 feet. However, this measure right here measures the height of the water in the tank, and it does change. We also need to measure the radius of the water layer, which also changes. And that would be this small r value, which is right here, measuring this r value here. There are 2 triangles within this one triangle, and they are similar triangles. If we look at the outer triangle, you can see that we have the full height of the tank, the full radius of the tank, and the slanted side. Because we have an angle at the bottom near the vertex and a right angle at the top, we know that the angle here in the corner is set by whatever 180 degrees minus 90 degrees minus the angle at the bottom is. There's another triangle in here as well, however, and I'll outline it now in yellow. That would be the height of the water, the radius of the water, and this portion of the slanted height. It also has the angle at the apex or the vertex, and it also has a right angle, which means that its angle here has to be equal to that angle there. We have 2 parallel lines cut by a transversal, and corresponding angles are equal. That means that the large triangle like this, where I have 6 feet here and 12 feet here, has to be similar to the smaller triangle where I have r feet here and h feet there. When you have similar triangles, corresponding sides are proportional to each other, not equal, but proportional. And this lets us write the following proportion, that the radius of the tank compared to the height of the tank has to be the same proportion as the radius of the water layer divided by the height of the water layer. This relates R as the height of the tank, or the radius of the tank, and H, the height of the tank, to the radius and height of the water layer. I know that the radius of the tank never changes. It's always 6 feet. The height of the tank never changes. It's always 12 feet. This then actually is giving me a relationship between the radius of the water layer and the height of the water layer. Let's go back to the information that we were given. We were given volume, radius of the tank, height of the tank, and we're asked to find something about the height of the water. It doesn't say anything about finding the radius of the water. So I would like the radius of the water to disappear. I used this proportion to write down a relationship between the radius of the water, lowercase r, and the height of the water in the tank, which is h. This tells me that r equals 1/2 h. My next step is to relate the volume of the tank to the height of the water layer in the tank, or rather the volume of water in the tank to the height of the water in the tank. Remember that the volume of water is given by the current height of the water. And as we saw in the previous problem, the volume for a conical shape is 1/3 pi r squared times h. And since we're only talking about the water, we use the lowercase r and the lowercase h. Now I can replace r with 1/2 h. This gives me 1/3 pi times 1/2 h quantity squared times another h. When I square 1/2, I get 1/4 h squared. The 1/4 times 1/3 gives me 1/12, or I can write it as pi over 12, and then I get h cubed. Now that I have pi over 12 times h cubed, I need to be able to take the derivative of it. When I'm looking at this particular one, I'm going to take the derivative of both sides of the equation so that I can figure out how the rates of change are related to one another. This is going to involve the chain rule. I'm going to rewrite my equation so that it's a little bit clearer when I take the derivative of both sides. I pull the chain rule, I pull the 3 to the front, and I get dv dt is equal to 3 times pi over 12, reduce the power on h by 1 to h squared, and multiply by the derivative of the inside function dh dt. Now I know that I want to find the volume, and so I'm looking for the volume when the height is 3 feet, or not the volume, I'm looking for the change in the height when the height is 3 feet. So I'm looking for dh dt. Let's go ahead and solve this equation for dh dt before we plug in. This tells me that I've got pi over 4 h squared times dh dt. By multiplying by the reciprocals, I can get then that dh dt has to be equal to 4 over pi times 1 over h squared times dv dt. Now I know that I'm looking for this particular value when the height is 3 feet and dv dt is -2 cubic feet per second. This gives me the following formula then. dh dt is equal to 4 over pi, the reciprocal of pi over 4, times 1 over 3 feet quantity squared times, and my volume was -2 cubic feet per second. When I work out the arithmetic, I end up with -8 over 9 pi cubic feet. Nope, not cubic, well, cubic feet over feet squared times seconds. Since I've got feet squared on bottom, it cancels 2 of the 3 feet on top, and I end up with -8 over 9 pi feet per second. Now I need to check the units to make sure the units make sense. I'm looking for dH dt. H should be measured in units of length, like feet, and time should be measured in units of time, like seconds. Does it make sense that dH dt would be negative? Yes, it does. As the water leaks out of the bottom, the height of the water will decrease, so dH dt should be negative, showing it's going down. Let's take a look now at the next problem, which is example number 8. At what rate is soda being sucked out of a cylindrical glass that is 6 inches tall and has a radius of 2 inches? The depth of the soda decreases at a constant rate of 0.25 inches per second. About all I got out of it was someone's drinking soda, which could be me since my favorite is Coke Zero. So what I've got is I've got a straw in a glass and someone is sucking soda out of the straw, which means that I must have soda in the straw or in the glass at some point. And later point in time, the glass is going to show less soda in it. And of course, this is the solid bottom of my glass. Now, there are some assumptions that you'll have to make in this problem without which you would have difficulty solving it. One of the assumptions that you'll have to make is that the 6 inches tall is referring to the soda in the water and not the height of the glass. Otherwise, you'd need to know how solid the bottom is and how deep that is. Let's start back at the beginning and write down all the information in the problem. At what rate? Well, that's got to be a derivative of some kind. D by dt of something is soda being sucked out, got it, of a cylindrical glass. Well, first, how would you measure soda? You measure soda in terms of volume. You don't measure soda in terms of length, and you certainly don't measure it in terms of square area. This has to be a volume problem again. So I'm looking for the change in volume of the soda with respect to time. It's coming out of a cylindrical glass that is 6 inches tall. By 6 inches tall, we're going to assume that they mean the height of the glass will hold 6 inches of liquid and has a radius of 2 inches. The radius of the glass is 2 inches. That's not going to change either at the beginning or later on. The radius will always be 2 inches, and the height of the glass will also always be 6 inches. The glass does not change dimensions. The depth of the soda, well, then you're talking about the height of the soda inside the glass. Well, now that is changing. Decreases. Yes, it would be decreasing. dH dt is equal to a constant rate of 0.25 inches per second, but it's decreasing, so it must be negative. We want to find the change in volume with respect to time. That's what we're looking for. I'm going to expect the change in volume with respect to time for the soda being sucked out is also going to be negative since it's decreasing the volume that's in the glass. That's all the information that's in the problem. What's left is for you to come up with an equation that relates the volume to the height. You're right, it's another cylinder. So that means that the volume of this equation is going to be pi r squared times the height. However, my radius never ever changes. So I can replace the radius with 2 inches. And then I square it inside the formula. This gives me that the volume is 4 pi square inches times the height. Now I'm going to take the derivative of both sides of the equation, and this gives me my relating equation for the related rates. I've got dv dt equal to, well, the 4 pi inches squared is just a constant. Only h depends on time. So I get 1 dh dt. Now I can simply plug in the value, and this tells me that dv dt has got to be 4 pi inches squared times a negative 0.25 inches per second. That tells me that I'm going to end up with a negative pi cubic inches per second. Do the units make sense? Inches cubed does measure volume, seconds does measure time. The units make sense. Does the sign of it make sense? Well, yes, as you suck the soda out, you should have less soda in the glass. So that means you have a negative. Now, if you're talking about the amount of soda that's now in my stomach, it would be positive since it has increased in value. So it depends on which problem you think you're solving. Let's move on now to example 9, which is an example that often stumps students when they're looking at these kinds of problems. However, example 9 is really not as difficult as it at first appears. The trick is understanding what it is they're asking about the rate of change in, and understanding how to relate the circumference of a rodden reel and the number of revolutions to that change. Let's read the problem. A fisherman hooks a trout and begins turning her circular reel at 1.5 revolutions per second. If the radius of the reel and the fishing line on it is 2 inches, how fast is she reeling in her fishing line? Well, first off, if you don't know what a reel is basically this picture here on the left. So you have a device on the left-hand side and you rotate it in a circle, which reels in the fishing line. So attached to this, somehow you have a pole, and along the pole is a line of fishing wire, and the wire comes down and you've hooked some kind of fish on the end of it, like that. As you reel this in by turning it in a circle, it rotates in a circle and winds the fishing wire back in to bring the fish close to the fisherman. So let's now go ahead and read the problem and write down the information we're given. A fisherman, got it, hooks a trout, okay, I've got one on the end of my line, and begins turning her circular reel. In other words, the fishing line is coming up and winding around this cylinder-shaped reel at 1.5 revolutions per second. Well, that sounds like a rate of change to me. A rate of change of what? Revolutions per second. So I'm going to write dr dt to represent the number or rate of change of revolutions per unit of time. This is 1.5 revolutions per second. I don't have anything on my picture to label, so I just write down the information. If the radius of the reel, well, the radius of the reel is basically the radius right here on the edge of that reel. And if I'm looking at that, let me see if I can make it a different color so it will pop out more. There we go. There's the radius on the edge. If the radius of the reel is 2 inches, and that's not changing, even though the fishing line is going on as well, how fast is she reeling in her fishing line? How fast is a change in position with respect to time? When you're looking at that, you're looking for a velocity of some kind, which means you have a length which is changing. The length that's changing is the length of the fishing line itself. So we can write down an equation for the fishing line. The fishing line is going to have to be the number of circumferences of the reel multiplied by the number of revolutions. So this is the circumference of the reel multiplied by the number of revolutions. If the circumference of the reel is, say, 3 inches, and I revolve it twice, then I've reeled in 6 inches of fishing wire. That's basically what we're talking about. Now I need to convert from the words into mathematics. What is the circumference of the reel? Where circumference of a circle is 2 pi times the radius of the circle. So this is 2 pi times r, where this is the radius of the reel. Then I multiply this by the number of revolutions, where I can represent this as capital R. Unfortunately, this relates the length of the fishing wire to 2 variables, lowercase r, the radius of the reel, and uppercase R, the number of revolutions. I was only given information about the rate of change of the revolutions per unit time, not anything about the radius, except I was told the radius is always 2 inches. So I can replace the radius with 2 inches, and this gives me 2 pi times 2 inches times the number of revolutions, capital R, which is 4 pi inches, capital R. Now that I have a relating equation between revolutions and length of the fishing line, I can take the derivative of both sides of the equation. This gives me 4 pi inches times the derivative of the revolutions with respect to unit time. Then I simply replace the dr dt with 1.5 revolutions per second. Now, revolutions is one of those weird units like radians that pops in and pops out when it's no longer needed. This ends up giving me 6 pi inches per second. Do those units make sense with length per unit time? Yes, inches is a unit of length and seconds is a unit of time. And it makes sense that as you're reeling it in, you've got a change in your revolutions. Now, it's not clear from the problem whether dl dt should be positive or negative, but think about it. If you're reeling in the fishing line is getting smaller, which means our revolutions should probably have been negative, which means that our change in the length should also be negative. However, on a problem like this, I would not count it wrong if you left it positive because it's not really clear from the situation. And I think it could be interpreted either way. This is the last example that I wanted to work in this video of basic related rates problems. There is another shorter video which works 2 very difficult problems. And I hope that this will help you on your related rates homework.